because that's the change. Okay, and we know that because the slope is changing over time, that means the rate of the reaction is changing over time. So it slows as the reaction progresses, for this one at least. Okay, why does that happen? Why does the reaction slow as it progresses? Because you use up your starting material, right? The principle is that the reduction in starting material concentration means that you can't produce as much product as quickly, and so the rate slows. And we have a rate law, what's it also called? Sometimes people call it rate expression or rate equation, right? And that is a mathematical summary of exactly how the rate changes with the starting material concentration. And in it we have K, which is a rate constant. That's just a proportionality constant. Concentration shows up in the rate law with an exponent. What does the exponent tell you? Okay, we call that the order, right? What are our choices for order? 0, 1, and 2, right? Okay. Things. We're going to talk even more today about how rates change with concentration. And what happens to the rate of a reaction is a function of what's actually happening in the reaction, including the energy of activation, potential energy steps in the pathway, right? Okay, so tell me, does the value of the rate constant affect the rate? You have to memorize that. What does the rate law tell you? Does the rate law tell you everything that affects the rate? If it doesn't show up in the rate law in one way or another, it doesn't affect the rate. That's the beauty of these equations. They summarize everything. Okay, so the value of the rate constant affects the rate. Does the activation energy affect the rate? It does. Where does it show up in the rate constant?
Okay.
Yeah, we're going to talk today about how the energy of activation actually is part of the rate constant. And there's a mathematical way of doing that. So when we're done putting all the equations together today, we'll include that. Okay, so what happens to the rate? What does activation energy have to do with the rate? It's going to influence K. But if I'm comparing two different reactions, and one has a higher energy of activation or higher than the other, what does that do to their rate constants and therefore to the rate? If the energy of activation is higher, what happens? It decreases the rate constant, which decreases the rate. Okay, how about concentration of reactants? That's one of the most important things, right? When you change the concentration of reactants, the rate slows. That's why the rate changes over time. Okay. How about concentration of products? Does that affect the rate? Now, the concentration of products doesn't necessarily show up in the rate equation because the rate equation only expresses what's happening to the forward rate, right? But conceptually, as your product concentration goes up, what happens to the backwards rate? It goes up. Does that influence your starting material concentration? Yes. So the rate of the backwards reaction does end up influencing the rate. And in fact, when we get to a 0 rate, what does that happen? That happens because the concentration of products is high enough that it causes the backwards rate and the forward rate to be identical to each other. Okay, so if we have a reaction A going to B, tell your neighbor whether it's going to be first order, second order, 0th order, or you don't really know.
It's like have some data. Yeah, I'll need some numbers. Yeah.
The message that I want you to embed upon your soul is that we don't actually know. And we don't know unless we measure it to figure out what the rate constant is. Or, as we'll find out today, if we know what the mechanism of the reaction is, then we can figure out from knowing what the steps are in the actual reaction mechanism, what the order would be. Now, this is kind of a circular argument because how do chemists figure out the steps in a reaction? Usually they figure it out starting with the kinetics. So we know the mechanism because we first figured out the rate law, which gave us clues about it. We'll talk more about that. Okay, so in order to get the order of a rate law for an individual reaction, we have to figure out what the order is by empirical measurement. There's two ways that we do that. One is the method of integrated rate equations. What's the other method? Method of initial rate. So let's talk about the integrated rate equations first. Tell your neighbor what those equations are, as briefly as possible, how you would use them to come up with them.
We're just doing that.
I've got that written down.
Like,
Just know that for
it's not like it says.
that's the other thing.
Okay, so the integrated rate equations are just the rate equations, then calculus is applied to those rate equations to convert them into a different form. And what that allows us to do is instead of this rate equation, rate is a function of concentration, right? But the integrated rate laws express the concentration as a function of time, which is the form that we actually think about the data in. Okay, now we have these equations, and if you look at all of the integrated rate equations for 0th order, 1st order, and 2nd order, what you'll see, the y-axis is concentration or some version of concentration, right? So concentration, natural log of the concentration, 1 over the concentration. Is a function of, or depends on how much time has passed, right? These forms of the rate law allow us to evaluate what happens to the concentration over time as a reaction progresses. Which is a pretty useful thing to do instead of just having the rate law, right? Okay. So we integrate the rate laws and we express them in a rearranged form that's the equation of a line. So what do the integrated rate laws tell us? They tell us that if the rate law is 0th order, then the concentration as a function of time is going to be what? Straight line, right? That's what the equation says. Y equals mx plus. Okay, so if we plot concentration versus time, normally, if we go back to here, this is what it typically looks like, right? Does it always look like that? It's possible to have a 0th order reaction in which the rate does not depend on the concentration, which would mean the slope of that plot stays the same all the time, right? Okay, so if we go back to the rate law, the 0th order integrated rate law says, you plot concentration versus time, you get a straight line. Okay. If we take our 1st order rate law and integrate it and rearrange it into the equation, the integrated form into the equation of a line, we get this, right? And that equation says, if you plot the natural log of the concentration that you measured versus time, you get a straight line with negative slope. Negative slope is equal to the rate constant. Second order says, if you plot 1 over the concentration. Okay. So the integrated rate laws are just another way to figure out what the rate law is by analyzing what happens to the concentration versus time. And it's kind of helpful because if we go back to a concentration versus time for first or second order, they're both going to be curved, right? How good are we at analyzing how curvy a curve is visually? That can be kind of tricky, right? It particularly can be kind of tricky if the data points have a lot of scatter. But if we instead compare the law of natural log of concentration versus time versus 1 over concentration versus time, only one of those plots will be linear for any one reaction. If it's first order, this one will be linear, and the other one will be curved. If it's second order, then this one will be linear. We can distinguish. Okay, so this plot is a summary of what you do to figure out whether something is 0th order or 1st order. So if it's 0 order, here's your 0th order integrated rate equation, which means you plot concentration versus time, you get a straight line. You can analyze it. Anything for 1st order. Okay, so you can use the method of integrated rates to come up with what the rate law is and the order of the reaction. How would you use the method of initial rates instead? So let's see if you can describe that method and how you would do it.
Remember correctly, this is when you have. And then there's gonna be like line over the first couple of lines. Yeah, with that you're able to.
I can't remember.
Double it, like the rate, double. Double it. Just got the first one. You know, with the
Okay, you should be able to do this. So essentially what we do is we say, we're going to pretend that the initial slope of a curved concentration versus time plot, that's pretty linear at the beginning. We're going to assume that those initial points, we can't tell the difference between the rate there and the rate at time equals 0. So we're going to make the rate of the first few points, the slope of those first few points, be equal to the rate at the very start of the reaction. Okay. So what we have here, the slope gives us the rate. We know what concentrations we started with, right? So in a single reaction, we know what the rate is as a function of concentration. And then you just redo it at a different sets of concentrations and see how the rate changes. And that tells you the order. And then you can use that data to do K. I think we're gonna, recitation 3, number 1 and 2, just asks you to use each of those 2 methods to figure out the rate law. Okay.
So I know a lot of times we said that the reaction is too fast, you can't get that initial rate. Could you use the rate as it approaches a final rate?
You don't know what the reagent concentrations are at that point necessarily. So you wouldn't actually do that.
Okay.
Okay. So we have these 2 methods. How do you know which one to use? So suppose you're in the lab and you're pretty sure you have a pretty slow reaction. Which method are you going to use? The method of initial rates could allow you to measure it in 5 or 6 hours instead of 3 weeks. So I would choose the 5 or 6 hours, hands down. How about the kinetics are super fast, but your instrument is not? If the reaction is really fast and your data collection is really slow, what are the chances that you can collect enough data in the fastest part of the reaction right at the beginning in order to get a good line? Pretty low, right? So that method. What method are you going to use instead?
Integrated rate.
Yeah, the method of integrated rate loss. So here is the actual experimental data that we used in recitation 2. This is collected at Harvard Medical School in 1995, I think. My husband collected that data, so that's why I have it. We have enough data in a part where the slope doesn't appear to be changing to use the method of initial rates here. So they couldn't use the method of initial rates, and they didn't. They used the method of integrated rates. Okay. Here's a third possibility. You have an unknown reaction. It's second order with respect to one starting material. It's first order with respect to the other starting material. You do the method of integrated rate equations here. Go back to our integrated rate equations here. What do you notice about them? How many different reagents concentrations will they analyze? Just one. So what if you're back to here? You can't easily use the method of integrated rate equations if more than one reagent is going to affect the concentration, right? Math doesn't work. And as long as you can use the method of initial rates for that, you're all good, right? Do that instead. Okay, but what if you have a complicated system with more than one starting material, and each of them are going to affect the rate? But you're in a lab that doesn't have a $2 million fast stopped flow kinetics instrument. You still need to know the kinetics. What do we do now?
Use the pseudo.
Yeah, we use the pseudo order. Okay, so we could cry. But that probably wouldn't help. So we're not going to do that. Okay, what we do is an approach that's described every time we use the word pseudo. So we say pseudo first order, a pseudo second order reaction kinetics. What we're talking about is a specific approach. Okay. So what we do is we set up our experimental conditions to mimic a 0th order reaction. Then set up our reaction kinetics so that we're approximating 0th order with A. So let's do it the other way. Let's suppose we approximate 0th order with B. Then we can measure the A concentration and analyze the order with respect to A by itself using the integrated rate equation, right? And then we can set it up again a different way to make A seem like or act like 0th order. And then use the integrated rate equations to figure out the order with respect to B. So the question is, how do you do that? Now, think about why a reaction is affected by concentration. It's affected by concentration because enough of the concentration of the starting material is used up as the reaction progresses for it to slow the reaction, right? Okay. So what if we make one of the starting materials in great excess, 100 times more than we need, or 1,000 times more than we need? Then as the reaction progresses, are we going to use up a high enough percentage of that excess reagent for it to actually slow the reaction very much? No, it isn't. So we're tricking the reaction conditions to make the rate think that the excess reagent is not going to influence the observed rate. So we're approximating 0th order for the excess reagent. Okay. And so then we can measure the rate and how it changes as a function of the reagent that's not in excess to figure out what's happening. Okay. So because the excess reagent mostly doesn't get used up as the reaction progresses, the reaction acts like that excess reagent mostly doesn't influence the rate at all. And within the scatter in the data, we can't tell the difference between mostly doesn't affect the rate and all the way doesn't affect the rate. So we get to pretend that it's 0th order. Okay, and then we get to use the integrated rate equations. We would do the reaction. One of them is in excess. And we figure out the order with the one that's the limiting reagent. And then we flip them to figure out the order with respect to the other one.
How
Yes,
do you know which one is limited?
well, you made up the cuvette with your concentrations in it. So you just go to the bench top and you put in 100 or 1,000 times more of one reagent than of the other one. So you have control over that. I probably won't, well, I don't know. Have you described those on an exam? We'll see. Okay, one more idea that you need to know. So we have talked about the fact that when the rate constant is higher, what happens to the rate? It goes up, right? So when the rate constant is higher, what happens to how fast the starting material gets used up? It goes faster, right? It would be nice to have some feel for how fast in terms of time it's actually used up, right? So we have this concept called chemical half-life. And that's just how long does it take to use up half of our starting material? So the faster the reaction, the shorter the half-life, right? Or the higher the rate constant, so the half-life, shorter the half-life, okay? So we have a relationship between the half-life and the rate constant. The actual equations just come from a rearrangement, careful rearrangement of the integrated rate. Okay, what we see is the half-life for a first order reaction is inversely proportional to the rate constant. This makes sense, right? When the reaction is faster, the rate constant is larger, so the half-life should be smaller. Conceptually, that makes sense, and that's what the math says too. Okay, for a first order half-life, does the half-life depend on anything other than the rate constant? Now, suppose you're on an exam and I ask you that question. Multiple choice. Does the rate constant depend on anything other than, sorry, does the half-life depend on anything other than the rate constant? Is it totally acceptable to go to the equation and say, well, the math says the rate constant is the only thing that influences the half-life? Can you do that? Absolutely. The equations summarize all of the concepts. And so if there isn't anything besides K that shows up in the half-life equation, then only the rate constant affects it. Now, we are going to talk about things that influence the rate constant, right? So what we can say is, if it doesn't influence or change the rate constant, it doesn't change the half-life. Okay, now we go to second order. What's the math say here? For a second order reaction, does the half-life depend on the rate constant? Yes. Does it depend on anything else?
Yes.
What is this? Square brackets around A with a 0.
Starting concentration.
Okay, so the square brackets mean concentration. So this means our starting material concentration at time equals 0, where time equals 0 reflects the start of the half-life. Okay, so think about this. After the first half-life, how much of our starting material do we have left? Half. What does that do to our second half-life? It makes it twice as long as the one came before. And then the third half-life is twice as long as the second half-life and 4 times as long as the first half-life. Because that's what the equation says if you think about how to read it. So first order half-life for a single reaction is always the same. First half-life and the second half-life and the third half-life, they're all the same length, right? They only depend on K. Does the rate constant K change over the course of a reaction? No, it doesn't. That's why we call it a constant, because it's a constant over the reaction. Okay, second order half-lives. So first half-life, certain length. When the second half-life starts, we start with half as much material as we did for the first half-life. So the second half-life is twice as long, and that continues. Okay, remember we've said conceptually that a second order reaction, the rate changes with concentration more than a first order one, right? Which means that the reaction slows faster as the reaction proceeds than the first order one, right? Which means the plot of the second order concentration versus time curve is curvier, right? Can you see how the curvature reflects half-life? All connected, it all fits together. Yes.
So on a test, would you give us, for example, like two graphs, one that's first order and one that's second, and we would just look at the curve?
If I gave you two plots that were both curved and told you that one was first order and one was second order, could you distinguish between first and second order? Yeah. If I just gave you a single plot, could you distinguish? Potentially, you could in your head break it into time periods and see if the concentration falls by half in each time period. It's a little trickier. You could do it. I'm not likely to make you do that, but I could.
You just explain like mathematically one more time why it gets longer every time for every half.
Okay, we switched to whiteboard here. So the half-life for second order is equal to 1 over A times starting concentration. So let's suppose we start with suppose we start with 100 starting material molecules. Okay, the first half-life we have a concentration that reflects 100 molecules. Okay. What's our second half-life? So after the first half-life, we only have 50 molecules left, right? So when we calculate the second half-life, we're dividing by 50 instead. We divide by 50 instead, what happens to this half-life? It's twice as big. Okay, the third half-life. What's the concentration at the start of the third half-life? 25. You see how the number keeps changing? Does that help?
Yes.
Okay.
Sorry, so I understand equation wise why first order it isn't that way, but conceptually I don't understand why it wouldn't be the same for a first order.
For you to believe the math.
I can do that, yeah.
Okay. So if we do the same calculation for a first order reaction. That's our equation, right? May change between the first and the second order half-life. So what happens to the half-life? That change. Things that I'm hoping that you'll get more comfortable with as the class progresses is the idea that you can read the math. The equations actually summarize what's happening. Now, let's go back to the first order one. Since the first since all the half-lives are the same length, right? Can we predict how much material is left? So if I said, I start with 100 molecules. Why don't we make it 200 molecules? Suppose we start with 200 molecules, right? How many molecules do I have left after 4 half-lives? So after the first half-life, we go from 200 to 100, right? Second half-life, we go from 100 to 50. by the time we get to the fourth half-life, we've gone from 50 to 25, right? So if we know the number of half-lives, we can calculate exactly how much time has passed. Or exactly how many molecules we have left, right? What if instead of 4 half-lives, I said 3.5 half-lives have passed? How many molecules do I have left? Can you do that in your head? Now, so here's the question. If half of a half-life has passed, does that mean I've used up half of the molecules that are going to be used up in that half-life? Is that my question?
Yes.
So what's the answer? If the first half-life uses up half of the molecules, does that mean halfway through the half-life I've used up 25%? You can only say that if this plot's linear. It's curved, right? So in a half-life, the first half of the half-life is going to use up more than half of the molecules. And the second half of the half-life, the reaction's moving slightly slower then, so it's going to use up less than half of the half-lives, right? Okay, so we need some kind of analysis based on the curvature of the plot that allows us to predict exactly how much we have left at points between exactly this number of half-lives. Does that make sense? Okay, so this works pretty well, except periodically it loses contact. So equations have all the answers, right? We can actually use the math to predict, because these equations, do they reflect the curvature of the plot? You actually know your rate constant and your starting material and everything else. For a first order reaction, the curvature of the plot is the same for wherever we are. Sort of. Okay, bear with me here. So we know the definition of a half-life. It's related to the rate constant. And we know the first order integrated rate equation expressed in linear form, right? That actually is a rearrangement of this. Okay, what if I don't want to talk about K, I want to talk about number of half-lives instead. Can I replace K with the redefinition of K according to half-life that comes from this equation? Sure. If I rearrange the half-life equation, I know that K is equal to 0.6, should be minus 6.3 over the half-life. I have a problem here with what I'm doing. When you rearrange it, you end up with this equation. What does the equation say? What's a square bracket subscript 0? This is the initial concentration. Start with when the reaction starts. What's concentration of A sub T? That's the concentration at the time you measured. Okay, if I take the concentration at the time I measure, or the time I'm looking at, divided by my starting material concentration, what's this ratio? That's the fraction of my original starting material that I have left at time equal T. Okay. And what that says is the fraction that I have left at a given time is proportional to T over T 1/2. What's T divided by T 1/2? That's the number of half-lives. So this reaction says, I can know the fraction of my original starting material I have left by knowing how many half-lives have passed. And you actually do that in your head easily for integer numbers of half-lives. You can do that math. But for non-integer numbers of half-lives, then we have to use that equation. Okay. So if you know the half-life, calculate how much starting material I have left at a given time. You can figure out A sub T. Can you do that same thing if you have K? Yeah, you can. You can also say, this is the percentage I have left. How long has the reaction been running? This is the half-life. And in experimental terms, you can say, how long would I have to run it to be 90% done with the reaction? Which would be helpful. What's the complicating factor with doing these little calculations? Sometimes you have to lift out these values inside the natural log function. How do you do that?
Raise to that power.
You take the other side of the equation and raise it to e. Okay, you will have to know how to do these calculations and be comfortable with them. So you should be able to use this equation to calculate your starting material concentration if you're given the concentration at a given time in the lives. Anything that comes out of this equation, you should get. Okay, so here we have nearly all of the relevant kinetics equations. Missing the Arrhenius equation. Many of you had a chance to look up the equation sheet that you'll use for Unit 1. What does it have on it? I don't give you the 0th order, 1st order, and 2nd order rate law because I'm convinced that you don't need help remembering those. I give you integrated forms, half-lives, and I give you some alternate versions of the integrated 1st order half-life. All right. I love this little summary. Turn to your neighbor and tell them what all of these different rows in this table have to do with each other. So can you progress from the first row to the second row? There's a logical conceptual progression within each one.
Next now. Yeah. Time and the next view. Yeah.
So we can do a straight actual. No, that's the fourth.
Yeah.
Integrate rate. Little chart of
Yeah.
the rate. So that's awesome.
Yeah.
Like we.
Exactly. I'm not sure about that one.
Yeah, and then wave, which is in the half line. Today is all gonna be okay. Like there's so many things that are okay, which affect our lives.
So your task, one of your tasks for today and tomorrow is to make sure that you can understand how all of those things are connected and where all of those things fit. If you're struggling with it, come to office hours and I'll go through it. Okay, are you ready for some new material? Believe it or not, that was not any new material. Feels different when you hear it later, right? Okay. So let's suppose we have a reaction that has starting materials A and B, product. The rate law says that the rate is first order with respect to A and first order with respect to B. Rates change when the temperature changes. So where does that come from? Which factor in the equation is temperature dependent? Okay, if I have a solution that contains A, and I bring it to the lab, and I put it on the Bunsen over a Bunsen burner, and I turn up the temperature on it, I heat it up, is that going to change the number of molecules in that solution? No, not unless the reaction is happening, right? Your concentration depends on how many molecules are there, and that doesn't depend on what the temperature is. So the concentrations are temperature independent, which means if rate changes with temperature, that must come from a change in the rate constant. So it's only the rate constant that's temperature dependent. Okay, a little review here. in order to understand why the rate constant changes with temperature, we have to go back to the energy diagram. So turn to your neighbor and explain the energy diagrams are, and see if you can answer these first two questions. Becomes relevant.
Come from.
No, yeah, totally.
So what we see is where on the y-axis reactants and products are tells us something about their stability, right? So if you have reactants that are lower on the y-axis, that means they're more stable and therefore lower potential energy, right? Okay. What makes one molecule more or less stable than another molecule?
How charged it is, or?
Okay, so I'm repeating this for the remote people. I'm not trying to summarize what you're saying. So what she said is how charged it is, for example. So remember in Chem 105 and you had to draw Lewis diagrams and there's all these questions about what is the best Lewis diagram, right? What are the things that affected whether it was the best Lewis diagram? One of them was formal charges. What else?
Resonance.
Say it again.
Resonance?
Resonance. How about, are the double bonds and single bonds and triple bonds of equal strength? And the strength of the bonds influences the stability and what potential energy is, right? So what we can say is the stability is affected by what the structure is, right? What does the Lewis diagram look like? What is the actual molecular structure? Are they double bonds? Are they single bonds? How is the molecule put together? That is what dictates where on the y-axis your starting materials and products, right? Okay. So does that change with temperature? If the stabilities come from the structure, if we change the temperature, are we going to radically alter the structure? No. Okay, so temperature doesn't change the concentrations of starting materials and products. Okay. The thing that's relevant, that's most relevant for the kinetics on these plots is the energy difference between reactants and the transition state energies, right? How tall that peak is, the energy of activation, that's what influences the rate constant and therefore the rate. So can we say that the more unstable that transition state is, the higher the energy of activation? Why would one transition state for one reaction have a different peak height than one for another reaction?
The temperature, like if it was a higher temperature, it'd make the peak lower.
Hold that thought, because there is a connection with temperature is going to play into what happens because of the energy of activation. Make a connection here. So the energies and stabilities of the reactants and products just come from what the molecule looks like. Is there a picture of what the molecule looks like for the transition state or the activated complex? So what's actually happening up here? If we could take an atomic picture of what was actually happening to the molecules themselves, we have to take apart the reactants and rearrange the atoms to get to products, right? Could we take a picture of what the atoms look like here? We could, right? So we're taking the atoms apart and we're rearranging them. And the part at which they're pretty much taken apart as much as they can before they start to come back together again, what they look like at that point, that's what the activated complex is. It's what is the structure of the transition state. Okay, so can you assume that different reactions will have the atoms and molecules looking different at the transition state than other reactions? So what determines the height of that activated complex is the structure of what's happening to the molecules in the transition state. Just like it's the structure that affects the abilities of the reactants and the products. Okay. Is temperature dependent or independent of structure? Somebody say it louder. Independent, right? Temperature is one thing, structure is another. So the energies and stabilities of the transition states come from the structure of what the molecules look like at that point in the reaction. Okay, so leads to the next question. Does the energy of activation change with temperature? It doesn't, because the energy of activation depends on how stable or unstable the structure of the molecules are at the transition state. And that is separate from temperature. So the energy of activation doesn't change with temperature. Okay, so can you tell your neighbor why would some reactions have a higher energy of activation than others?
Wrong verb.
I'm talking to myself.
Yeah.
So,
And depending on the difference between the active and reactant. It will be a huge hill there.
So some reactions will have a higher energy of activation than others. So because the energy of activation depends on the starting material energies, and that's going to be different between different starting materials, and on the transition state energy, and that's going to be different between different reactions because what the molecules will look like will be different at that point. Okay, so the energy of activation doesn't change with temperature. But this is what we do know. Okay. We do know that the higher the energy of activation, the slower the reaction can happen. Why would that be?
Lower probability that they would reach
Josh,
that.
say it louder.
Lower probability that they would reach that state, the transition.
Yeah.
state.
At a lower temperature, well, in order for molecules to react, they have to go from the starting material energy. They have to gain enough energy to get to the high energy transition state before they can go to products, right? When you raise the temperature of the solution, you're giving the molecules more energy. There's more energy available to them. So they're more likely to be able to make it over that barrier. Or another way of saying that is that at a given temperature, only a certain percentage of the molecules will have enough energy to make it to the transition state so they can make it to product. And so only a certain percentage will react. If you raise the temperature, what happens to the percentage that can react? It increases, so the reaction goes faster. Okay. So if we're comparing two different reactions, the one that has the higher energy of activation will have the lower rate, right? Okay, but those are, go ahead.
So in our textbook, you said that higher temperature always increases reaction rate, but then
For one kind of reaction.
for it.
So if I take one kind of reaction and I run it at 3 to 4 different temperatures, which one's going to be the fastest? The higher temperature one. Is that always true? Always. It is always true.
What about with like when we were doing Gibbs-free energy, sometimes you'd increase the temperature and it would make Gibbs-free energy positive, and then
Okay, but Gibbs free energy depends on comparing reactants to products. Doesn't depend on how fast you can get there. Yeah. Okay. Comparing different reactions, the higher the energy of activation, the slower the rate for those two different reactions. But if you take one reaction, you have one reaction, will the energy of activation be the same no matter what temperature you run it at? Yes, but if you raise the temperature, which temperatures will be faster? Always the higher ones, right? Okay, so let me explain in a little more detail why that is the case. Take a deep breath. Let go some of your Chem 105 angst and let go of all of any worry that you have that maybe you didn't remember something you should remember. Okay, so I'm going to assume that none of you remember anything. Kinetic molecular theory says that all molecules are moving all the time, right? And at least for a gas, the energy associated with that movement is defined by these equations, where the kinetic energy equals 3/2 AT per K of the Boltzmann constant. It's not a rate constant. Isn't that rude how the same symbol can be used for two different things? It's rude, but in the context, you have to know within the context, kinetic energy, this is the Boltzmann constant, not the rate constant. Okay, the kinetic energy is also equal to 1/2 the mass of the molecules times the square of their average velocity. Okay, this equation here says, as you raise the temperature, what happens to the average velocity of molecules? Right? Okay, so the greater the temperature, the faster molecules are moving. And the greater their average kinetic energy. But, you may or may not remember this from Chem 105. Are all of the molecules moving at the same velocity? No, there's a distribution of velocities. We call that a Boltzmann distribution. Okay, here is a representation of a Boltzmann distribution for a single gas at 3 different temperatures. So we have the number of molecules as a function of the velocity of individual molecules. What does the plot say? This red line says that you have more molecules moving at lower velocity, right? Compared to this blue dotted line. On average, the molecules are moving faster, right? You also have a greater range of velocities. So the point is, we'll answer the question, which one's at the highest temperature? The curve that has more molecules moving at a higher velocity is the higher temperature one. So the blue line is a higher temperature and the red line is the lowest temperature. So this plot shows what you already know, which is as the temperature goes up, you have more molecules traveling at higher velocity. Why does that matter? Most reactions happen because you have a collision between molecules, right? And they have all of this energy associated with their motion, and then they collide, smack into each other. What happens to their velocity?
Stops or decreases.
Where does the energy associated with that velocity go? It goes into potential energy. So they smack hard together, and that energy associated with their velocity is what gets translated into a higher potential energy to go up to a higher energy transition state. Okay, so what that means is, in general, the faster molecules are moving when they collide in order to start a reaction, the more energy is available to them to go over the energy of activation barrier and go to product. Okay, but since molecules are traveling at different temperatures, all of the molecules collide with enough power to make it over the energy of activation barrier.
Yeah.
Only some will, right? What percentage? Fraction of those molecules that collide with enough energy to react depends on the temperature and on how much energy they need to react, right? So it depends on both the temperature and the energy of activation. Okay, so we can say when a collision happens, only a certain number of them are going to collide within a certain percentage, say, could collide with enough energy to actually react. So we're tracking the kinetic energy of each particle. It's a distribution, the velocities are a distribution, right? if you raise the temperature, you increase the range of kinetic energies. And you increase how high the kinetic energy is. So only a portion is going to be able to react. It's going to make it over that energy of activation barrier. But if you raise the temperature, what happens to the fraction that has enough energy? Okay. So what we know is rate depends on the energy of activation and on the temperature, right? Answer that question. This should say higher energy collisions are more likely to have enough energy. Exactly. The answer here is all of the above. Because what happens is you increase the temperature and that increases the kinetic energy, all of the molecules. It also increases the percentage of molecules that have enough kinetic energy to collide with enough power to make it over the energy of activation. So if you increase the temperature, you're increasing the number of molecules that could possibly react when they collide. Okay. So take home message. Reactions work better, go faster at higher temperature. Now, this is my second favorite equation in the whole universe. Not the one that I would have tattooed on me if I were having a tattoo. So do you ever watch people walk around with tattoos? And I don't actually, aesthetically, I don't appreciate tattoos. Doesn't mean other people can't. But it's been a question, what would you tattoo on your body if you could tattoo them, right? I love plants, I might put a vine or something on me. But actually, I would want something on my body that expressed some grand truth that I believed in, that made a difference to the world. So I would actually tattoo delta G equals delta H minus T delta S on my body. That is my first favorite equation. I don't think I would put that in a place where anybody could see, because how would you explain that to like the server at a restaurant? Okay, so my equation that I still love but probably would not tattoo is the Arrhenius equation. So we've talked about all the things that influence the rate with respect to energy of activation and temperature. That what the Arrhenius equation tells us. So there are a couple of things. K is the rate constant that shows up in the rate equation. Temperature, P is temperature. This is our energy of activation. The R here is just the gas constant R. Okay. So what the Arrhenius equation says, well, okay, what's A? Okay, it's called the frequency factor, which we'll talk about why that is. Sometimes it's called the pre-exponential factor. Why would they choose the name pre-exponential factor? It's a proportionality constant that in the Arrhenius equation comes before the exponential term.
Oh.
So it is the pre-exponential factor. If that helps you remember the name. Okay. It turns out that we can link everything in this equation except the gas constant R to something that is true about how a reaction works. So each of these concepts, each of these values, energy of activation, temperature, and A, tell us something profound about how reactions happen. And by knowing what those numbers are for a given reaction, that helps us understand what's actually happening in that specific reaction. So if we go back to all of collision theory, molecular motion, energy of activation, what has to happen for a reaction, Arrhenius equation actually teaches us about all of those things. Okay. One thing to keep in mind here as you read the equation. The Arrhenius equation is typically expressed as a negative exponent, right? How would you express it as a positive exponent? Can you do that? Somehow.
Just flip it.
If you take the negative sign and turn it into a positive sign, all that does is flip the numerator and the denominator in the exponent. The reason that I'm talking about that is that it's a lot easier to read the relationship between the concepts. if you have a positive exponent. Okay. What if we're reading it in terms of positive exponents? What happens to the calculated value for K when the temperature is a larger number? Up. You already know that that's true? You already know that when the temperature goes up, the rate constant goes up, which makes the rate go up. And look, the equation tells you the same thing. Okay. What happens to the calculated value for A when the energy of activation goes up? Energy of activation goes up, fewer molecules at that temperature will have power to make it over the energy of activation barrier. So the reaction will slow because what happens to the rate constant? It goes down. Is that what the equation says? So this whole idea of what happens to the percentage of molecules that can make it over the energy of activation and how that changes with temperature, is that embedded in this equation? Yeah, it is. Okay, let's see. A actually tells you something profound as well. Okay, here's a question for you. Let's assume that the energy of activation is really low and the temperature is really high. So every time molecules collide, they have enough energy to make it over the energy of activation barrier and react. Is that a possible scenario? Sure. Under those conditions, will every collision lead to product? Why not?
Structure.
It depends on the structure of the molecules. So think back in your head, Chem 105, valence bond theory. Bonds form by overlapping orbitals, right? Okay, suppose you need to form a new bond between the atom on one molecule. Part of one molecule needs to react with the other molecule. In order for that to happen, orbitals have to overlap, right? Well, what if orbitals have to overlap this way, but the collision happens this way? Are we going to get to product? Even if there's enough energy, am I going to get to product if the collision happens backwards of how it would have to happen in order for a bond to form? No. Okay, so the answer here is, do all molecules with sufficient energy react every time they collide? No, they don't. Do some reactions? For some reactions, is it possible for every collision to lead to product? Yeah, well, actually some you can. So some reactions, the actual spatial orientation of how the collisions occur doesn't matter. So that under that condition, every collision with enough energy leads to product. But other reactions have a very high requirement for exactly how those orbitals are going to have to overlap in space in order for the reaction to happen. So this frequency factor or pre-exponential factor A is different depending on whether all collisions of sufficient energy lead to product or not. Or in other words, A is different depending on whether for this particular reaction, things have to line up exactly right so the orbitals are all pointing exactly the same way when they collide. Okay. So go back to what this means. Arrhenius equation says, if you look at the actual exponential factor here, this exponential factor essentially says only a percentage of molecules can react because those molecules have to have enough energy to make it over the energy of activation barrier. And that depends on the interplay between the temperature and how high the activation barrier actually is, right? Isn't that what this exponential factor reflects? So if we're just looking at the exponential factor, say only a fraction of the molecules can react, right? But This exponential factor only talks about the energy of the collisions, a function of temperature, and whether that's enough to make it over the barrier. But the pre-exponential factor, or the frequency factor, tells you what fraction of those collisions that have enough energy could actually leave. Now, A actually isn't a fraction, it's a number greater than 1. It also considers how many total collisions there are likely to be, but together, the combination of A and the exponential factor tell you that only a fraction of the fraction of molecules with enough energy to react will actually react to form product. Okay. So, yes.
And it's from A that we actually get the units for K, right?
That's a decent question. So the question is, from A, do we get the units for K? So here's the thing. Can we use units? Can we take, like if we have units for energy of activation, which is joules per mole. We have units for temperature, which is Kelvin. What happens when you take the X, when you take the E to those things with units? Those units anymore? A is the number that also is units. So where do the units of K come from? We make them up according to the order of the reaction in order to give us a rate of molarity per second. The only time where you can't actually. Okay. See if you can summarize those the answers to those questions. Neighbor.
Yeah. This ST will react.
Say decrease. Oh, yeah, awesome. So yeah, decrease. Oh yeah, awesome. G higher than activation energy. Activation goes up. It's O.
Structure.
Your constant will go down. Rate of reaction energy. Change. Increase. I guess what it is.
Yeah, if it's the same.
Let's start with the third question. Will the energy of activation increase? So as temperature increases, just say it out loud. What happens to K?
Increase.
It increases. So what happens to the rate? It increases. As the energy of activation increases, if we're comparing two different reactions, what happens to the rate constant? Rate constant goes down. What happens to the likely rate? It goes down. Okay. Will the energy of activation increase if you change the conditions of the reaction? No, the energy of activation only depends on the energy difference between starting materials and the transition state, which only depends on the structures of the starting material and the transition state. So we can change the conditions of the reaction, which means concentration or temperature or what the solvent is. It's not going to make a difference to the energy of activation. Okay, why do different reactions have different values for the frequency factor? Different reactions have different mechanisms, right? They happen in different ways. They come from formation and breaking of different kinds of bonds. And those different kinds of mechanisms and different kinds of bonds have a different requirement for spatial and geometric overlap of the orbitals to make and break those bonds. That's a long answer. Do you want a shorter answer? Different mechanisms have a different requirement for spatial orientation in order for a product to form. And therefore, they have a different values for A. Okay, if we compare the A values for different reactions, what can that tell us?
I just have the question with A. So that is the percentage of molecules that will overlap, correct?
Well, it's a proportionality constant
So it's not.
that is smaller when a smaller percentage of collisions are oriented in the right way to come to product. I don't know if that helps you or not.
I thought it would be less 0 to 1. always, but you said it's a value over one,
Well, A actually comes from two different things. It's actually the fraction of collisions that occur in the right orientation times the total number of collisions. So when you're thinking about it in terms of the fraction that collide in the right way, the right spatial orientation, you're thinking about it the right way, but A itself is not the fraction because it has another factor embedded in it. And you don't need to really understand that as well, although I am going to talk about it next time. So it's totally acceptable to say that A reflects the fraction of collisions that happen with the right orientation to lead to product. But A itself is not a fraction. Does that make sense?
That's what that's there. So it's like, oh,
Okay, if we compare the A values for different reactions, what can that tell us?
2% actually.
If one has a high A value and one has a low A value, what does that tell you? The one with the higher A value is not as sensitive to the directionality of the collisions as the other one is. And when we get down to the level of mechanism, that can tell us something. We're going to talk about a little bit about that. Don't you all wish you had mutton chop? Like Arrhenius?
Looks like
There is actually a cute little family in my ward whose last name is Arrhenius. Because I'm a geek and because this is my second favorite equation, I was really excited when they moved into the word. I was also excited because cute little sister Arrhenius, actually, her parents live next to my parents in a small town in Raymond.
Could you repeat what you said about comparing A values for different reactions?
Okay, so let's suppose we have two reactions. One of the reactions, in order for the collision to lead to product, there has to be like this careful overlap of orbitals, which means that the directionality of the collision matters really a lot. What's going to happen to the value of A? Is it going to be higher or lower?
Lower.
Lower. Okay. In contrast, you might have another one that pretty much any collision will collide in the right way to lead to product. So what happens to the value of A then? It's higher. Yeah. Yes.
Does that mean that if there is, if it doesn't matter as much, the orientation of the collisions, then you'll get more product? So could you see that?
Yes.
in the graph as well?
You won't see it as the graph, you won't see it in the energy diagram, but it'll show up as a higher rate constant. Okay, so one way to interpret the rate equation is to say, here's our rate equation, but we know that K is actually a factor of the it comes from the pre-exponential factor, the energy of activation and the temperature, right? So we can rewrite the rate equation this way. Does this rate equation tell you every blessed thing that influences the rate of a reaction? Yeah, it does. All in one place. Kaboom, there it is. So tell your neighbor every possible thing that influences the rate. Why it makes a difference to the rate.
Or frequency factor. Yeah.
So.
Picky did. And then, yeah. The temperature, the higher temperature, the higher the rate.
Really touching. Like what it all
Based on the combination of the Arrhenius equation and the rate expression or the rate law, there's four things that affect the rate. Okay. Which one of them, which one of these things affect the rate because they alter the rate constant? And which ones affect the rate without affecting the rate constant?
So the only one that doesn't affect the rate constant, but affects the rate is the concentrations.
Yes, so the only way we can influence rate without changing the rate constant is to change the concentration. Okay. Which ones affect rate because they alter the rate constant? All the rest of them, temperature, energy activation, and requirement for specific orientation. Now, if we are running a specific reaction, there's only two things we can do to increase the rate. At least according to where we are here. Can we influence the value for A directly? No, it's set by the mechanism of the reaction. Can we influence the energy of activation?
No.
No, it's set by the mechanism of the reaction and the structures of the starting materials and transition state. So if you're setting up a reaction, what do you have power to do to make the reaction go faster? Increase the concentration or increase the temperature. The rest are set by the mechanism of the reaction. Dying and need a break?
Yes, yeah.
Okay, we'll talk about how chemists figure out what the values for A and energy of activation are.
That is not super. You're just saying not all, when you have a certain temperature or something, not all of it.
A lot of times. Calculations, but just one is going to run out before the other. The context that you don't know yet. Actually,
No, it's just the hat, I guess.
how much product with that equilibrium.
How's it going? I saw you somewhere.
I saw her last week.
Somewhere else?
No, no, not in this
Like from before class.
Instead of one rate, we might-
So I guess did you, the one, so.
Yeah, I go there a lot.
Remind me your name one more time. That's right.
Wait, sorry, I didn't even say I'm Abby. I'm Abby. What's it?
That was a real.
Hard enough. Thank you.
Thank you.
Growing up, I like never met it.
Not seeing the right song.
I'm a sophomore.
Yeah, that's what I was thinking too.
Annie, what did you say?
Who wants Annie?
Like open this up and that. Hungry. True.
Shit.
I'm completely afflicted. The elevator lady said, do you have to swipe?
Okay, so we've done a lot of talking about the energy of activation, right? The energy of activation makes a big difference to the rate. When we start to talk about mechanisms, the energy of activation will tell you something about what the transition state looks like or what's actually happening in the reaction as you move into products. So how do we know what it is? Like I've shown you an energy diagram. I'm going to start out studying a reaction. They don't know what the energy diagram is yet. So how do they know how tall to draw the peak? They have to measure the energy of activation using the Arrhenius equation. Okay, how do we know what A is? My mom is really smart. She's even has some science background. It's an embarrassing thing. So my dad actually was my high school chemistry and physics teacher. Very small high school. He was the only science teacher other than the biology teacher. So actually, my parents have a fair amount of chemistry expertise. My mom started out as a physical sciences education major. So if anyone could ask their mom, maybe I could. My mom's not gonna know, right? What do you do? Yeah,
This may seem like really dumb, but you just draw like Lewis structures and see which is the best one.
so we can speculate about maybe what's happening, but we don't actually know what the transition state looks like yet, so we can't. Think about what's happening here. Do I know? Can I measure K? So remember when we measured to figure out the order of reactions in the rate law, we can use the method of initial rates and we can use the method of integrated rate equations. And can we figure out K? Yeah, we can. Okay, this equation says K changes as a function of temperature. Can I run the reactions at different temperatures and measure K at all those different temperatures? Yes, and when I do, I can tell you how K changes as a function of temperature. So what do you bet there's a way to analyze this equation and work it around in order to analyze the data that you get K as a function of temperature? Well, I probably wouldn't be asking that if there wasn't a way, right? Okay. Well, we can take this Arrhenius equation and we can do to the Arrhenius equation the same kinds of transformations that we did to the rate laws. So we can use some calculus on it. Doing. Take the natural log of both sides of this equation. You get natural log of K equals natural log of A plus what happens when you take the natural log of E to something? E goes away. So we have what the exponent was, minus A over R times 1 over temperature. Okay. This is an equation of a line, right? So what this tells us in the line that we're looking at, let's see. If our X value is 1 over the temperature, and our Y value is natural log of K, we should get a straight line, right? So what we've done experimentally, we've measured K at a whole bunch of different temperatures. And then we plot the natural log of that rate constant versus 1 over temperature and get a line. Or well, we get a bunch of data points that look like a line, right? But can we get the equation of best fit of that line? We can. And the slope of that line, we're going to take the equation of best fit and map it to this equation. So what's the slope of that equation of best fit of the plot of natural log of K versus 1 over temperature? The slope is minus the energy of activation over R. So do we have a way of measuring the energy of activation? We're not measuring it directly, right? But we're pulling out the value for energy of activation from data that says, how does K change with temperature? And when we plot it in the right way, we can get the energy of activation. Okay, how do we get the value for the frequency factor A? Well, the y-intercept is the natural log of that. So if we take E, raise it to the power of the y-intercept, then we know what our A value is. Okay. How many experiments would you actually have to do? How many measurements would you have to do to get here? How many experiments do you have to do to measure, get the rate constant at a single temperature? Well, using the method of initial rates, that would be 3 measurements, right? 3 experiments. And then you'd have to do it at a whole bunch of different temperatures. Probably 4 would be a good number, a good small number. So we're talking 12 measurements in order to get the energy of activation and the y-intercept. Okay. So it's not a trivial thing to do, but you can do it. Okay, here are the curves of best fit from data obtained from 2 different reactions. So we measured the rate constant as a function of temperature for 2 different reactions. And then we plotted natural log of K versus 1 over T for both of those reactions. One of those reactions has a higher energy of activation than the other. How do you know? So what does our slope equal?
What's that?
The absolute value for the slope equals minus energy of activation over R, right? Negative or positive slopes? These are negative slopes, okay? So the steepest one is going to have the largest negative slope, right? Okay. Can we say that the steepest one has the highest energy of activation? Yeah. What this equation says is the line with the steepest slope corresponds to the highest energy of activation.
What does the natural log of A tell you? Oh, that's the y-intercept.
Yeah, so if you have the y-intercept, like I could say, which one is going to have the higher y-intercept?
One.
Probably the blue one. So the higher y-intercept is going to have the higher value for natural log of A, which means it's going to have the higher value of A. So I could give you a plot like this and say, which of them is most sensitive? For which of them is there a higher requirement for careful geometric alignment of the molecules in the collision? So this gets complicated because there's so many up and down things to analyze, right? So when A is higher, what does that tell you? It tells you that the geometry of the collision matters less, right? So the blue line, the geometry of the collision matters less because the y-intercept is higher. And the red one, the geometry of the collision matters more because the y-intercept is lower, so A is lower. So yeah.
Is the rate of red higher than the rate of blue because the activation energy is lower?
We don't actually know the rate because we don't know what concentrations we're talking about. So we're only looking at rate constant here, right? Okay, there are actually two different ways that we can find the energy of activation. Both of them use this log version of the Arrhenius equation. The one we just talked about, you measure K at a bunch of different temperatures, plot natural log of the rate constant over 1 over temperature, pull out the slope of the curve of best fit, and that gives you your energy of activation. Okay, but this takes a lot of experiments, right? You have to do a lot of measurements in order to be able to construct a plot like this. What if you don't really care how well you know the actual number? You just want to know, is the energy of activation pretty high or pretty low? You can actually just do two measurements from two K values. Figure it out. Okay. Take this equation, and there's a version of this equation that just compares the rate constant at two different temperatures. But you get this ugly beast here. That's useful because from a rate constant at only two temperatures, you can come up with a reasonable energy of activation. I just want to show you where that 2-point linear Arrhenius equation comes from so that it makes more sense. Okay, let's suppose we have the equation at two different temperatures. There's an actual number. So if this is one temperature, there is a physical K value that corresponds to that reaction at that temperature, right? We do that at two different temperatures. And we subtract the two equations from each other. When we subtract the two equations from each other, what's going to disappear? Will the A value be the same at those two different temperatures? Pretty much, yeah. A value does not change with the temperature. So if we subtract them, we have plus natural log of A minus natural log of A. So the natural log of A falls out of the equation. You don't even have to worry about it anymore. And we get something that looks kind of ugly like this. We can simplify the right-hand side of the equation. This will look like this. Now keep in mind, one thing that kind of throws students for a loop is that when you go online or in the textbook, there are different versions of this equation. Some of them have a minus energy of activation. Some have a positive energy of activation. Both of those work just fine. If I carry this negative sign through here, that's the same thing as flipping the position of the T1 and the T2 here. So this equation has a positive sign, T2 minus T1, is the same as the one with the negative sign, T1 minus T2. Same thing, it's just expressed in a different way. Okay, now you may or may not remember about natural logs, that if you subtract the natural logs of two numbers, that's the same thing as taking the natural log of the ratio of those numbers. So we express this as a ratio of those numbers, and we have this equation. Now, notice this form of the equation that has a positive sign in front of the energy of activation, whatever you define as 1 or 2, if there's a positive sign here, then 1 is in the numerator, 2 is in the denominator. 2 is subtracted from 1. If you add the negative sign, it's the same thing, except now it's 1 over T1 and 1 over T2. Okay. The only reason that I bring that up is just make sure that you're using one or the other of these versions and not putting a positive sign and flipping. On an exam, you'll have the equation. Just make sure you're putting your numbers in the right place. That's all. So we have this equation. How do we use it? What that tells you is if I know the K values at 2 different temperatures, I can calculate the energy of activation, right? If I know the energy of activation, and I know one of the K values at one temperature, can I calculate the K value at the other temperature? Absolutely. The only potential mathematical barrier here is that you have to get the K1 and the K2 out from inside the natural log function. Remind your neighbor how to do that. Okay. This is ugly, right? If I was in an exam setting, I could put all the numbers on the page in the right place, but me being me, what's the percentage that I could type all those numbers at once into my calculator and actually end up with the right number? Approaching 0 in my personal life, okay? So when you have something that's as ugly as this with as many numbers to put in at once, I tend to calculate E over R and calculate 1 over T2 and calculate 1 over T1 and put those numbers in the equation and solve it stepwise where I don't put all the numbers in my calculator at once. Now, there may be some of you in the class that can use your calculator faultlessly, including all the relevant brackets. What percentage of you is probably in that position? Not 100, right? Probably less than 10%. So take the extra time to write those multiple lines so you can break up the math. Because what you really don't want is to know how to do it, understand the concepts, put in all the numbers at the right place, and then write the wrong number down at the end because of what your calculator did. That's not where you want to be. Crap, we're not moving fast enough. We will have to do one of those on the recitation. Okay, let's see how fast we can get through the material, and then I'm hoping there's still time to do recitation. Let's talk about reaction mechanisms. So what's a reaction mechanism? A reaction mechanism is just what steps happen in the reaction as you go from starting materials to products. What bonds break? What bonds form? What order do they form in? Do we form something that then is converted to something else? It's just, tell me the sequence of events that happens from starting material to product. Okay. Now, up to now, all of the energy diagrams that I've showed you have had one bump in them, right? Those correspond to a single transition state between starting materials and products, right? A one-step reaction. But actually, you can have multiple steps in a chemistry reaction, in a chemical reaction. And each step will have its own peak in an energy diagram. Okay, the individual peaks we call elementary steps. And when you have one elementary step, you take your reactant, you pull it apart some way or another, go through a transition state to form something different. But notice that this something different isn't stable. The reaction can also proceed through another transition until you finally get the product. Okay. And the structures of what forms in the middle, those are called intermediates. Okay. The reason we care is that we can figure out what the elementary steps are, then we know what's happening in the reaction. And if we know what's happening in the reaction, that's the whole goal, right? Okay, so here we have hydrogen gas reacts with nitrogen monoxide to form nitrogen gas and water, right? The mechanism says that reaction actually happens in two steps. First step, hydrogen reacts with nitrogen monoxide to form dinitrogen monoxide. That's water. Dinitrogen monoxide isn't the final product. So there's a second step where the dinitrogen monoxide reacts with an additional hydrogen molecule to form the final products. Okay, so what are the elementary steps? How many elementary steps are there? Two, right? Terminology, net reaction. What is a net reaction? So the net reaction only includes the total number of starting materials and the total number of products. Okay, in this case, hydrogen is a starting material. Nitrogen monoxide is a starting material. But this hydrogen is also a starting material. Okay. And to tell your neighbor what the intermediate is and how you know that it's an intermediate.
Outside. Just the end. It's just chilling there.
So an intermediate is a structure that's formed from the starting materials, but isn't one of the starting materials. So when we make up this reaction at the benchtop, we don't add nitrogen monoxide to our flask. It's formed from the reaction. Okay. And it's made in one step and then used up as a sort of starting material in the next step. So we recognize an intermediate because it doesn't show up in the net reaction. It's produced in one step and consumed in a subsequent step. Okay. Step one and step two. How many steps are there in our energy of activation, in our energy diagram? How many bumps are there going to be? Two. Which bump is taller? The slower one is taller. So what we have here is a tall peak for the first slow step, and then an intermediate form, so there's a local minimum, and then a shorter peak for the next step. So which one makes the biggest difference to the rate? The slow one. How do you know? Tallest one. Yeah, the highest peak. Okay, so this slow step, the one that has the highest peak in the potential energy diagram, we call that the rate determining step. Why do we call it that? Because it's the one that controls the rate the most, right? So we call it the rate determining step. The rate determining step is the one that is relevant to the rate law. Where does the order come from? Comes from the rate determining step. And anything that happens after the rate determining step doesn't influence the rate at all. So the whole rate here is determined by the first step and then the second step. Once we get to here, we'll go on the product. So one way to visualize the rate determining step is to say, because it has the highest energy of activation, it's sort of the bottleneck in the reaction. So here is a visual picture If the first step is slow, that's the first step, this one here, the first step is the rate determining step, right? Does it really make a difference if these funnels get a little bit bigger or a little bit smaller? No. Okay, here. Does the size of the first funnel potentially make a difference? So that little middle, the teeny middle funnel, that makes the biggest difference, right? But does it make some difference if this gets smaller? Yeah, it could. Okay, so the things that happen before the rate determining step do actually influence the rate some. The things that happen after don't at all. Okay, here are energy diagrams for different mechanisms. How many elementary steps? 1. Yeah, okay. Which is a slow step for this one? First step. So the second and third steps don't influence the rate. That's a slow step. Second one doesn't influence the rate. The first one kind of could here. I wouldn't want to do the analysis of that last one myself. Okay, here's the connection I need you to make. So we definitely told you that you couldn't use the stoichiometry of a reaction and make it equal to order, right? Okay, and that's true, and that's why we have to measure it. But stoichiometry does actually influence the order. You know, the slow step, the order of the reaction comes ultimately from stoichiometry of the rate determining step. So one of you, I think last reading quiz, asked me the question, I know that the stoichiometry of the reaction doesn't determine the order of the reaction, but how come sometimes the stoichiometry is the same as the order of the reaction? Well, this explains it. If you have only a single step in the mechanism, what's the rate determining step? If your reaction mechanism is a single step, then the order of that single rate determining step is the order of the rate law, which does match the stoichiometry of the reaction. But if you have more than one step in the elementary step in the reaction, then you're going to have reagents that don't necessarily show up in the rate law with the order that's equal to their stoichiometry. Okay, so the rate law tells us what's happening in the rate determining step. So step back for a minute and say you're investigating an unknown reaction and you're trying to figure out what's happening in the reaction. Is it one step or is it two step? How high are the energies of the rate determining step? Is the rate determining step first or second? We can get all of that information. Oh, neat reaction. The rate law tells us what's happening in the rate determining step. Okay, so here we're back to the same reaction. What's the rate law? So first, what's the rate determining step? Rate determining step is the slow one, so it's the first one. Okay, so the order of the reaction is equal to the stoichiometry of the rate determining step. So what's the order with respect to hydrogen? 1. What's the order with respect to nitrogen monoxide? 2. Now we know the order of the reaction. In Chem 106, I'll show you something like that and then say, give me the order of the reaction. In actual experiments, we always do it the other direction. We say, what's the order? Okay, that's going to tell me something about what's happening in the rate determining step. So what does the energy diagram look like? The tall and then small. Okay, so think this through. Suppose we have a reaction, A plus B goes to C. And we figure out the order of the reaction and the rate law using either the method of integrated rates or the method of initial rates. And we find out that it's first order A and first order B. Does that tell us anything? It tells us that in the rate determining step, we're involving both starting materials in the same step. What does that tell us? Is it possible to do that reaction in a single elementary step? Yeah, it is. So we have one molecule of A, one molecule of B are involved in the rate determining step, which tells you both reactants are present in the transition state of the rate determining step. So there could be a single step in the mechanism. Okay, what if it's the reaction is first order with respect to A and 0th order with respect to B? What's happening in the rate determining step? Only A is involved in the rate determining step, right? So is it possible to have only a single step reaction here? It isn't. So because only A shows up in the rate determining step, that means when B shows up, it has to be in a step after the rate determining step. So there has to be at least 2 steps where A is involved in the first rate determining step and B is involved in a step after the rate determining step.
So the multiple, in the equations with multiple reactants, if we say B is 0th order, it doesn't necessarily mean that it doesn't have an order. It could have an order in its own elementary.
Yes, it means it doesn't show up as an order in the rate law. But that doesn't mean that it doesn't have a stoichiometry in an additional step. Okay, yes.
So rate law helps you determine the stoichiometry for the rate determining step. I forgot my question,
Let
actually.
me give you an example and see if it'll help. Okay, some of you have had Chem 351 already. You, at that point, probably cried tears over SN1 and SN2 reactions and E1 and E2 reactions. Those of you that haven't, doesn't mean anything to you. SN1 stands for substitution nucleophilic unimolecular, and SN2 stands for nucleophilic substitution that's bimolecular. So when organic chemists began studying reactions, they were studying different types of reactions. And there's this kind of reaction called a substitution reaction, where you take a carbon chain that has what they call a leaving group. It has something on it, often a halide, in this case bromine. And you can take another group and you can make them swap places. So it's a substitution reaction because what happens is, say the hydroxide comes in and substitutes for the bromine and the bromine leaves. The bromide leaves. So what's happening is, suppose you have something like this. What happens is the carbon bromide bond has to break, and then you form a bond using the electrons on the hydroxide, form a new bond to carbon. Okay, this is what chemists noticed. When you change what they call the degree of substitution around the carbon that the bromide is bonded to, the reaction acts different. So this is the same reaction on paper, except the hydrogens become methyl groups, right? So chemists thought those reactions should act the same way, right? Both of them, you have to break a carbon bromine bond, and you have to form a carbon hydroxide bond. If they act the same, and they go by the same mechanism, what should be the case about their rate laws? They should be the same, right? So if they're the same mechanism, they should occur with the same number of elementary steps and the same rate determining step and have the same rate laws. What did they see? Not the same rate laws, right? Okay, and what the chemists figured out is how many big bulky methyl groups go around this central carbon actually changes the mechanism. And we know the mechanism has to be different because this is first order with respect to both starting materials. And other reactions, only first order with respect to the substituted bromide material, right? Okay. What does the difference in kinetics tell us? They have to be happening by a different mechanism. And actually, you can figure out or speculate about what the mechanisms might have to be. So take this, the second order reaction. It's first order with respect to both starting materials, which tells us what's in the rate determining step. Both starting materials, right? So that tells us the things we know have to happen in the reaction, if we go back to here, is this carbon bromide bond has to break, and you have to have hydroxide forming a bond to carbon. if both the hydroxide and the starting material are involved in the same step, then all those have to happen in the rate determining step, right? Okay. So what kind of mechanism could we imagine that would match that second order rate law? How about this one? Suppose the hydroxide comes in and starts to form a bond with carbon. How many bonds can carbon make? 4. So if you start to form a bond to this carbon, what has to happen? You have to make another bond break. So what happens is the hydroxide comes in, and as it comes in, it pushes out the bromide. Happens all in one step. Okay, another interesting thing. Do you remember the concept of antibonding orbitals from molecular orbital theory? What happens when you put electrons in an antibonding orbital? Break the bond, right? So this is what happens. The antibonding orbital for the carbon-bromine bond extends out the back behind the carbon-bromine bond. And so the hydroxide comes in from the back, inserts an electron pair into the antibonding orbital of the carbon-bromine bond, and that makes that bromine leave because it breaks the bond. Tricky, right? Okay, here's a question for you. Does the geometry of how the hydroxide collides with this other molecule make a difference? Yeah, so what kind of A values are we looking at here? Low ones, relatively speaking, because it has to align, the orbital that contains the lone pair has to line up exactly with the antibonding orbital in space of this. Okay. How did chemists come up with that mechanism? First, they measured the rate law, and then they measured the energy of activation and the A value, and they said, oh, okay, that makes sense. So the energy diagram would look kind of like that. And they measured the energy of activation, it's not super high. How would they have measured the difference between reactants and products to construct that energy diagram? You remember doing calorimetry in Chem 105? From calorimetry, you could measure the delta H of reactions. So by combining calorimetry measurements to get the delta H, and kinetics measurements to get the rate law, and therefore the number of steps and the energy of activation, now we have an energy diagram for that reaction. Comes from the kinetics ultimately. Okay, how about a first order reaction? The rate law for the first order reaction says the first rate determining step only involves this starting material, right? So where must the hydroxide show up? It has to come in a second step after the rate determining step, right? So here is a proposed mechanism. We know we have to break the carbon-bromine bond, right? So in the first step, in the rate determining step, where this shows up, what happens is the bromine leaves on its own. Bond breaks, and we're left with an open shell carbon that we call a carbocation. Okay, this carbon wants to make a new bond, right? So then the bromine comes in, puts its lone pair into the open orbital, and you get a product. Now, is there any geometry of collisions required here? Not in the rate determining step, right? So what kind of value for A are we looking at, high or low? High, yeah. Transition state. The first step only involves carbon-bromine compound. It's a slow step because it shows up in the rate determining step, highest energy of activation. You form a carbocation in the transition step and go to products. So can you see how the kinetics is part of what chemists use to figure out how a reaction happens? It's actually really important. And when you combine the measurements of energy of activation that we just talked about with calorimetry to get the delta H, you can construct a whole energy diagram, and that gives chemists a feel for what's actually happening in the reaction. Okay. there is one way that we can change the mechanism of a reaction. So remember I said, the energy of activation, we don't have any control over that, right? It's set by the mechanism. But there is something we can do sometimes to change the mechanism. And we can add something to the reaction called a catalyst. It changes the way the reaction happens. It makes the mechanism be different in some way or another. It either radically changes the structure of the transition state, so the transition state structure is more stable, so the energy of activation is lower, so the K is higher, so the rate goes faster. Or it makes the reaction happen a whole different way, and the energy of activation is lower. Okay, so what is a catalyst? It's something that we add to the reaction to make it go a different way that's faster. The catalyst doesn't change the starting material and it doesn't change the products. It just changes how we get from starting materials to products to let it go in a faster way. Okay. The other thing about a catalyst is present, it's involved in the reaction, but it doesn't change the products. So it doesn't actually, in the end up reacting with something, which means it doesn't show up in our net reaction that only includes starting materials and products. Okay. Example of, well, let's see, go back. Catalysts are recycled, so they're used in one step and produced in another step. So every time one net reaction happens, you've used the catalyst, but you also produce it. Does, over the course of a reaction, does the concentration of the catalyst change? No. Okay, and if the concentration of the catalyst doesn't change over the course of the reaction, as the reaction progresses, does the concentration of catalyst that we start with influence, does it slow down the rate over the course of the reaction? It doesn't. So catalysts don't show up in the rate law. They act like they're zero. So you can add a catalyst and you still have the same number of elementary steps, or you can add a catalyst and you change the mechanism by making a different number of steps. So this black line, this black curve, that was a single step, single elementary step reaction with a fairly high energy of activation, right? Then when you add the catalyst, which path will the reaction take instead? So someone says red. Why would the molecules choose to go the red pathway instead of the black pathway? Because it's a lower energy of activation. So it's easier for the molecules to go the red path faster. It's more likely to happen because the energy of activations are lower. So when you add a catalyst, those molecules will go through the lowest energy path, which happens to be the path with the catalyst. Okay, if you're given a reaction mechanism, so we have our net reaction, and our net reaction includes starting materials and products, right? It doesn't include intermediates, and it doesn't include catalysts. How do you tell the difference between those? How do you recognize an intermediate from the sequence of elementary steps? So an intermediate is produced in one step and consumed in a later step. What do you think a catalyst is? It's the opposite. It's consumed in one step and produced in a later step. So you have to look at the elementary steps to figure out. Okay, so here we have net reaction, 2 ozone molecules decomposed to form 3 diatomic oxygen molecules. The actual mechanism, this is the one that you did in your reading quiz today. The actual mechanism is the first step, chlorine reacts with ozone to form monochlorine oxide, monochloro-oxide, something. And in the next step, it reacts with an additional ozone molecule to form the products. Okay, which one, what's the intermediate here and what's the catalyst? So first thing you look for, both intermediates and catalysts don't show up in the net reaction. So the things that are not starting materials or products are chlorine atom and the CLO, right? Which one is a catalyst and which one's an intermediate, and how do you know? Tell your neighbor.
Makes sense.
So the intermediate is something that's made in one step and used up in the next step. So the intermediate is CLO. The catalyst is first used and then produced. So the CLO is a starting material in one step and a product in another. That means it's consumed and then produced. So the chlorine is the catalyst. We just answered that question. Okay, if the first step were the slow step, what would the energy diagram look like? Draw it with your hand. The first step is the tall peak. The second step is the smaller peak. What would the rate law be? So the stoichiometry of the rate determining step becomes the order if it's the first step. So our rate law here, let's see, let me draw it. So if we're just looking at our first step, rate determining step, we have a rate constant, and we have our concentration of chlorine shows up and our concentration of ozone shows up. That looks great, except for what?
Catalyst should.
The catalyst acts 0th order. So even though it shows up with the stoichiometry of 1 in the rate determining step, we know that it actually doesn't make a difference to the rate over time. So we cross the catalyst out and we're just left with first order reaction with respect to ozone. Okay. Okay, if the second step were the slow step, what would the energy diagram look like? Draw it with your hand. We go small peak, big peak. So we did if the first step were the slow step. What would the rate law be? What's the rate law of the second step?
I just have a question. So the net reaction had a 203. Why would that not be 03?
Because that second ozone is only involved in the step after the rate determining step, so it doesn't show up in the rate law.
Okay.
Okay, so we did, if the first step were the slow step, what would the rate law be? First order with respect to ozone. The second step is the slow step, what would the rate law be? So if the second step were the slow step, that's a different mechanism. Has a different energy diagram, and it's going to have a different rate law. Okay, so the question is, how do we define the rate law if the slow step is the second one? So let's do it. We have this, right? So go back to first principles and we say, okay, I know that the order of the reaction comes from the stoichiometry of the rate determining step, right? Is that right? The answer is yes and no. The rate laws have to be defined in terms of concentrations that we have control over. So you have to define a rate law from starting materials that you can go to your chemical cupboard, get off the shelf, and make a solution out of. When we make a solution of the CLO, not one of our starting materials, is it? It's an intermediate. So we can't include CLO in our rate law. So now what do we do? Because actually that is the stoichiometry of the rate determining step. How do we do this? We can't do that. Okay. So what do we do now? My favorite picture. That's so sad. Okay, so we have a problem. When the slow step is the second step, then we have to use an intermediate, but we can't use an intermediate because that's not allowed in the rate law. So what do? What do physical chemists always do when they have a problem? They always do math and algebra, right? So what math and algebra can we do to pretend that we're actually physical chemists? we look to the math, right? So what do we do here? What we do is use algebra to calculate the concentration of the intermediates from the concentrations of starting materials. Okay. So this is what we have. And what we have to do is find a new way to algebraically define the intermediate concentration in terms of starting materials that we actually could start with. Okay. So if the first step is fast and the second step is slow, is it a decent bet to say, I bet the first step comes to equilibrium before the second step is really happening? We can say it. Okay. So we say if the first step is fast and reversible, then it reaches equilibrium quickly. Which means we're assuming that the first step comes to equilibrium before the second step has to really happen. And what we can do is say at equilibrium, the forward rate and the backwards rates are the same as each other, right? What would the forward rate of the first step be? It would be equal to a rate constant times the concentration of ozone, first power, chlorine to the first power. The backwards one would be the concentration of intermediate to the first power, oxygen to the first power. Okay, set them equal to each other. Now do we have an algebraic expression that we can rearrange to come up with an alternate definition of our intermediate concentration? We can. We do a little bit of rearranging and we get that kind of ugly. So this is the rate constant for the first step forward, and rate constant for the first step backwards. There's like these little microscopic rate constants. Okay, so we have that whole definition for CLO. We take what we started with as our rate law, and instead of CLO, we put all of this junk in it. And we combine all of our rate constants, and we get that. Take all those rate constants, and we multiply them and divide them. What do we get? Another constant. So we call that K total. Is this our final rate law? We have to get rid of our chlorine, right? Because it's still the catalyst. So we end up with that. Okay, when you see a rate law that has some concentration in the denominator, what does that tell you? We have concentrations in the denominator in a normal rate law? No. So if you have a rate law that has concentrations in the denominator, what you know is it came from something uber ugly like this. So that meant that the rate determining step was second, and you have to do some stand on your head to get to it. Okay. Tell your neighbor the answers to these ones. Slow step is the first step. How do you express the rate law? In that case, the order of the rate law comes from the stoichiometry of that first slow step. If the slow step is not the first step, then what do you do? Look to the math. There's my verbal description of it. I won't read it to you. You can go after class, map in your head what would happen, just what it says there. Okay. Give me 5 minutes. So chemical catalysis does a bunch of important things, right? It lowers the energy of activation, often by changing the mechanism. It can speed up a reaction so fast that a process that couldn't happen in our lifetime can happen. So for example, in your body, you have chemical reactions which are required for your metabolism that if they were just carried out in a flask on the bench top, they would never happen in your lifetime. But because your body includes enzymes that are catalysts, you can speed up those reactions to be something that actually is useful instead of something that takes so long that it's never going to help. Okay. Catalyst can be applied to infinite number of reactions because it's not used up. And the difference that it makes, so the rate constant for the catalyzed reaction compared to the rate constant for the uncatalyzed reaction can be millions or billions or trillions. That's how fast it can improve the rate. Okay, I want to share with you best metaphor for the atonement that exists on the face of the planet. That's a high claim, right? Okay. So let's talk about mortality. What is the goal of mortality? What's the process that we're supposed to go through? Start out as natural man, right? Where do we want to end up? Man of Christ, right? A different person. You can call that mortal man or natural man to celestial man or son of man versus son of God. There's lots of different words we can use for it, but there's a transformation, right? So if we were drawing the plan of salvation and the requirements for us as an energy diagram, how would you do it?
A huge energy of activation barrier.
Exactly, huge energy of activation. But first, okay, let's see. What a really thick pens.
Yeah. It's definitely.
Let's go to the board here.
Some people say
An energy diagram, so potential energy is the y-axis. Instead of the course of the reaction, let's do a time frame, right? Start out a natural man. What's the stability of the product? More stable or less stable? Less stable.
More stability.
So don't think about how much energy it takes to get there. Think about the end product. Is it more stable or less stable than where we are now?
More stable.
Way more stable.
Yeah, maybe it is.
I think so anyway. Okay.
Heat is just very evil.
Those of you that, like me, are fully committed to following the Savior and doing this process, learn something very quickly. And that is trying hard enough does not get you there. Anyone else had that experience? Okay, so on our own, if the mechanism is we're going to take our energy and our determination and our focus and the skills with which we are born and just decide to get from here to here, how well does that work? Won't happen in our lifetime, right? And why won't it happen? Because the energy of activation is too high. It takes more energy and more power and more focus and more skills than a single one of us possesses. Okay, and let's suppose I can try really hard and I can get closer on the pathway by trying hard. You ever had that? You think, this semester I'm going to do everything right. You can do it for a little while. The energy of the potential energy of doing it by deciding is really high, right? The truth is that the actual curve, even if we have a little intermediate where we're better off and closer to the man of Christ than we were before, energy of activation right? So, and we can sit at that intermediate where we're better than we were before until what happens? So we have to use up some of our potential or emotional or intellectual energy, or something happens and we have less energy. We get sick, we have a fight with our roommate, or we have conflict with our spouse, or we have a bout of depression, or something difficult happens. And then what happens to the charity and the kindness and the compassion and the stability? Is it easier to go forwards or backwards? It's easier to go backwards. And lots of times, what do? We go backwards. Now, that doesn't reflect our commitment. It doesn't reflect our desires. It just reflects the nature of the process and the fact that the energy of activation it would take to actually get there on our own by deciding larger than we actually have. What is our only option? We have to change the mechanism, right? Doing it this way, just by trying harder, great tragedy of mortality that it doesn't work that well. Okay, so we have to change the mechanism. The only way we know to change a mechanism is a catalyst, right? What is the catalyst? Our relationship with the Savior and the blessings of the atonement are the catalyst. Okay, so when we fully covenant to serve the Lord and enter the path that includes spiritual gifts, so we enter in through the gate of baptism, we bring the Spirit into our lives, we have the change of heart that Alma talks about. What happens to the mechanism? Changes. It changes because the Savior is the catalyst. If we go back to here, I think it's really interesting that chemists talk about how the starting materials and the catalyst have to have intimate contact. That's the actual verbiage that they use. And when we have intimate contact with the Savior, what happens? You can do it with a different mechanisms. Now, does that mean the energy of activation is low? No. Does that mean that the reaction and the change happens necessarily in the time scale of our lifetimes? Probably not. But the process becomes something that we can actually make progress in because the change, the reaction, is catalyzed by the Savior. And now it's actually possible. Okay. So when we change the mechanism, does that change the energy of activation? Yes, it does. It changes the energy of activation. Okay. Now for a chemical reaction, with a given energy of activation and with a given catalyst, there are things that you can do to increase the rate. You can increase the temperature, right? We have control over that. And when increasing the temperature, what we're doing is increasing the energy available to the starting materials to engage in that process. So what can we do as natural man or covenant people of Christ to increase the energy required to help us over the energy of activation barrier? Is that the function of the Spirit of God in our life? All the things we do that bring the Spirit into our life are functioning like raising the temperature on a reaction. We're giving ourselves more energy to make it possible for us to go over that barrier. So I think the spiritual equivalent of increasing the temperature of the solution is doing what? All of the primary answers. Pray, be kind to others, do service, read the scriptures. We're still not doing it. We're not going to make it over that barrier because we're praying or because we're reading our scriptures or because we're doing service. We're only making it over that barrier because we have intimate contact with the catalyst who's the Savior. The better we know him and understand him, the more the Spirit and his power can change us. Fix our understanding, adapt to what we do. But the Savior's doing it because we can't do it by ourselves. Is that the best metaphor ever?
Yes.
Thanks for listening to that. I'm sorry we didn't get to do more recitation. I never know whether to talk more and have you discuss more or whether to do more recitation. See you next time. Come to office hours on Monday and get help if you need to. Oh yes, please leave those. I will sort through them and mix them and all of those things.
think we're